Well, hello, everybody online. I hope everybody's safe and sound at home, and sorry we can't be here face to face. But I wanted to talk today about what we call an IPU processing and AI at the edge. And to start, I think it's interesting when you ask people what the edge is today, there's sort of a perception of, the mobile device is the edge. And when we're looking at the mobile device as the edge, then apps are relatively slow and they can tolerate long latency. Most of these apps are sort of initiated by and curated for humans. So it's people that are driving in it, and the response times that we expect are human-based response times. So hundreds of milliseconds is acceptable, even a second or 2 seconds. But I think this is really an example of Hoyle's principle, which is things are the way they are because things were the way they were. So in other words, when we have a network which was relatively slow and relatively long latencies, the applications that developed were suited for that sort of network. But where we're going really is 5G and IoT, and it fundamentally changes what is going to be possible at the edge because all of the conditions change. So as we get high bandwidth, as we get low latencies, as we're able to slice the network bandwidth and make different quality of services available, you can still have human beings using their mobile devices at much lower latencies that are acceptable. But meanwhile, we're going to have self-driving cars and robotics that are going to be operating next to a human being, that it can't kill the human being. We're going to have cameras with massive data flows, and we're going to have lots of AI at the edge. So these new Internet of Things at the edge will be everywhere. And instead of humans curating them, they're going to be on and generating data all the time, not just when the human pushes a button. And they won't be supervised by human beings. So they will need to sense, analyze, and react to the world in real time, constantly, and make decisions at the edge, not the humans making decisions. They'll need to do it quickly, intelligently, and securely, every time and all the time and always. So it really requires a fundamental change in computing. So edge is really not a mobile device. The way that we view edge is much, much larger. It's really taking the core of the cloud data center and bringing all of those features out to the edge in a server. And this requires a new compute model for AI and edge. And the two fundamental things that are being added here are a GPU and an intelligent IO processing unit, what we call an IPU. The GPU is critical for running the AI and machine learning workloads. So edge applications, intelligent IoT devices, all of that needs to run. But that also needs really an intelligent IO processing unit to feed the AI and ML and edge applications, and not just to feed it, but to securitize it. So in other words, to make all of those IoT devices secure. As soon as you start adding IoT devices, all bets are off. This is no longer in your data center, it's at the edge. People are going to be plugging things in that may or may not be trusted. You need to validate those, authenticate them, etc. Very high bandwidth, low latency access. So really it's an extension of what we see happening in the core today. And we need to line up and add these two key new elements to the edge server. So what I thought I would do here is look at the evolution of cloud computing and then see how that impacts the edge. And to start, it's almost embarrassing sometimes when I look at some server vendors that are still focused on a server that is really at least a decade out of date today. And that is that the focus is solely on the processor, the memory, and the storage. And IO is almost an afterthought. It turns out that the network is really, really important. So enterprise data centers today, okay, they support virtualization. That's a technology that's at least 15 years old now. It's nice, but really kind of sleepy and looking backwards. we're moving towards a software-defined network and software-defined security and software-defined storage. But if enterprises still treat the server as sort of this generation of server, they will continue to lose business to the cloud. So the cloud has really built something that's a cloud-native edge server. In the telco world, they call this a MEC, and that really adds a couple of key elements. So first of all, the GPU is central to edge and AI and machine learning sort of workloads. The storage is very smart, it's very fast, it's software defined. So we're seeing things like NVMe, SSDs. The memory is interesting. It hasn't seen as much innovation as some of the other areas, but persistent memory is out there. People are starting to look at it. I put a question mark that maybe it's going to be there, maybe not. It's still too expensive relative to flash, for example, and not as fast as DRAM. But on the infrastructure side and the software, everything is containerized, it's fully software defined and hardware accelerated. And the key thing here is that the IPU is there. So if we look at the way this model is developed, I put the cloud computing model, the first gen of is 2008. I think Amazon AWS actually started in 2006, but really got underway in around 2008. And basically it was a virtualized machine. So it was supporting VMs and it had a hypervisor, and the load on the CPU was relatively small. So that CPU load was basically, maybe a core that was running some of the hypervisor. Wasn't a lot of overhead. And the IO here was 10 gigabits per second. So pretty good for the time, but relatively slow. Fast forward, we started to see in 2013 timeframe the explosion of what's called software-defined networking. So as we needed to talk between virtual machines, we had software-defined networking running on the CPU, but it started to chew up lots of CPU cores. So the cores were actually switching packets between virtual machines. The network sped up as well. So we have 10 to 40 gigabits per second in that time frame. So we're really starting to use up some CPU cores. Fast forward and we become containerized in the 2016 timeframe. So VMs are still important, but the storage also becomes smart and software defined. And this puts even more pressure on the CPU and the network. So we're moving up now in the 2016 timeframe. We start to see 25 gigabits per second and 100 gigabit per second networking. But we're consuming more and more of the CPU as storage becomes software defined and higher speed networking. And then we start to build security into the network, and we see security happening everywhere. And this consumes even more CPU cores to do the software defined security. And on top of that, we add a GPU. And that GPU accelerated computing is great, but it needs even more data to feed the beast. So it puts more pressure on the network. And suddenly, your CPU core usage is so high that you're actually seeing huge inefficiencies in terms of what the cloud was able to offer. And so the last step here is where we're going, where we have everything is containerized. You really want to offer your customer bare metal isolation. And to do that, we see an IO processing unit coming into play, where all of those software-defined functionalities, at least the data path of that, and now also with an IPU, the control path, is being moved into this IO processing unit, or IPU. And when that happens, all those penalties that we're taking away from the ability of the x86 core to run applications suddenly free up. And so this is the key breakthrough, is that the IPU is critical to unleash the GPU AI workload performance and really all containerized app performance. And it provides bare metal isolation so that if the x86 is compromised by a rogue app, it still allows you to keep all of your security and service provider policies. And this is the cloud compute model. And what I'm going to argue is that the edge is no longer just a phone. It's really an extension of this core cloud compute model that will be moving to the edge. So what Mellanox builds here to address this, our IPU, this is the second generation, it's the Bluefield 2 processor. This is something that we talked about in the fall and said we'd be sampling, and now we're doing that. The A72 ARM cores are critical to being able to support the control path and provide that isolation that I talked about. But what's really important is actually the other three things that I've sort of highlighted here, which is the ConnectX-6 subsystem and all of the security that's built into that, the hardware root of trust, regular expression engines. It turns out that all of the data path acceleration is running on those blocks. All the A72 CPUs is important for isolation, but if you're going to try to run the data path on an ARM core, then really you haven't changed the fundamental equation. If you're bringing an x86 CPU to its knees, then you're going to bring an ARM CPU to its knees. So the point is not to shift the data path processing from an x86 to an ARM. That's a failed proposition. The point is to provide an isolated, secure domain that we can operate the control path in, but to do all of the acceleration in what we call software-defined hardware accelerated. And that's what I'm going to talk about for the rest of my talk. So this traditional data center security model is really just protecting at the edge. It's securing north-south traffic that's going into the data center. But when we move into the cloud, and even more as we move into the edge, what we see is that we can no longer live with just a next generation firewall and maybe a VPN with SD-WAN being secure. Everything needs to be secure. So we need intrusion detection and prevention. We need anti-malware. We're going to see SmartNICs and the IPUs that are built, that are used to build those SmartNICs everywhere. They'll be protecting storage. They'll be protecting containers, VMs, across east-west traffic, inside of web servers. The east-west traffic is equally as important to protect now as the north-south traffic. So it's no longer sufficient just to protect the ingress and egress of data that's going into and out of the data center. The entire edge data center needs to be secure. So here's some examples of what we've been able to do. This is a software version of connection tracking. Connection tracking is something we built with JD.com. We've submitted that into the Linux world. It's fully integrated into OpenStack. It just works. And what we have here is software-defined but hardware-accelerated connection tracking with what we call ASAP squared. So if you want to use an OVS firewall driver to provision OpenStack security groups, we can do that, and we get nearly 20x performance improvement by doing that. The other thing, we just recently announced an acquisition that we made of a company called Titan IC in Ireland. They do a regular expression processor. And here we can do massive parallel search. We can do wildcards, classes, induction, and there's a huge number of applications that apply to the edge here where we can recognize the application that's running. We can detect intrusion. We can detect malware with signatures. We can do data loss prevention and even intelligence search. So this is another example where we're accelerating the data path. This is a very detailed example of where we can even be looking at emails, for example, and detect specific things that we want to look for. We can do up to 1 million rules running in parallel on a SmartNIC to accelerate the hardware. And the applications for this extend even beyond that. We're going to put this inside of wide area networks. We're going to put it into DDoS engines, intrusion, IPS, IDS systems, data loss prevention, and even software-defined routers and networking. So this Titan search acceleration is a critical part to an IPU processor. And things like Snort and Suricata, this is an IPS IDS system. This is an example of where we can integrate into existing open source projects. And we're interested to work with all sorts of the guys that are doing this to accelerate this with our IPUs. And lastly here with the Titan search engine, we can even do intelligent computational storage, where instead of having the database read massive amounts of data from the storage and then do the searches locally, we can do that remotely and use an intelligent device as a storage controller. So that's where we're going with that technology. And really, when we pull back up to where we started with the 5G edge applications, one thing that is really important is the vRAN. So this is called a radio access network or a virtualized radio access network. There's all sorts of different ways to implement that. So you can have distributed units, you can have what's called a radio head-end, which here is called an RU. You have a centralized unit, which is more centralized. And then altogether, this is running on what the telco community calls an MEC, which is a multi-access edge computing. I would argue that that is simply an extension of the core servers that we find inside of core cloud functionality. So really, this isn't a different beast. This is the same beast. It's embracing and using all of that same capability. And we think in this sense that the telco community and the edge will be able to benefit from all the development that's happened in the cloud and leapfrog past the traditional simply virtualized machines and go into a cloud native architecture. So that's really the vision that we see here. An example that we've shown previously with our partner NVIDIA, you know, they are really a pioneer in software-defined radio and doing vRAN. They talked about this at the Mobile World Congress Americas last fall, where they have their EGX platform, which is running an aerial SDK, and it accelerates all of the, you know, traditional baseband controller functionality that you need to run on a radio. So instead of the radio head ends being way up on the top of a tower, now you have really just a radio that provides digital data to a server. And all of the radio functionality is done in software. And to do that, the radio, remote radio head end needs very high performance communications back into those servers. And the key things that it needs is time slicing, low latency, very accurate timing if you're doing distributed radio. It needs everything to be secure. And as we start to look at applications like automotive and cameras, and we need to be able to validate all of those endpoints. And so the ability of the Bluefield 2 IO processing units to do all of the security acceleration, the authentication, to have a hardware root of trust, really enables things like the EGX to perform effectively. So when we secure all of those links and we add all of the real-time elements that's needed to slice this with very, very low latencies, you need something like an intelligent IO processing units to accomplish all of that. So we're working with partners like NVIDIA and many others at the edge to be able to do the security, the real-time transfers, the low latencies, and the high performance, and to provide an isolated security domain independent from any applications. And ultimately, we can see securing everything, even the data models in AI, and that's going to be important for the edge as well. So that's our view of the IPU and its role inside of building a secure edge for the next generation. It's really not just the phone anymore. It's an extension of the core cloud computing into the edge. So with that, I'll open it up for some questions.
Thank you, Kevin. Okay, we've got a couple audience questions, and I've got a couple questions of my own, so I'm going to jump in here. So if I can arrange my windows. You mentioned ASAP squared, the connection tracking offload. And I know that that's built into ConnectX, but here you're talking about the IPU or Bluefield. So I assume that they have different connection scale between what you can do kind of on chip with ConnectX and what you have capability to do with Bluefield. Is that correct?
Yeah, so, you know, it's interesting. Mellanox comes, the answer is yes, but, you know, Mellanox comes from a legacy and really a heritage of building supercomputers and solving the world's largest compute problems. And as a result of that, we could never build enough memory on chip to maintain the states for the types of problems that we're trying to solve, because we're doing massive scale out. So really from the very beginning of the company, every resource that is on chip is a cache, every resource. And anything that we do, we can always spill to external memory. So when people ask us, how many connections can you support? We sort of say, well, millions and millions of connections. And we will always spill to external memory. In the case of a regular NIC, like the ConnectX family, that can be host memory. In the case of a smart NIC, it can be host memory or local memory that's DDR connected to the blue field. But in any case, we have massive scale. And frankly, we can scale up for any of these things, whether it's the Titan regular expression engine or whether it's our ASAP squared engine. We can do massive scale, and we're doing that. Our customers are using us with millions of connections.
Okay, got it. So in the case of ConnectX, if it's a standard NIC, you'd be crossing the PCIe interface to host memory, maybe a little bit of a latency hit there. And in the case of Bluefield, that's on basically the memory attached to Bluefield. Exactly
right. And so it's really the miss penalty. If you think of the traditional cache architecture in a processor, the miss penalty is higher if we're using a ConnectX than if we're using a Bluefield. But really it has to do with the locality of reference. In this case, temporal locality. If you have a lot of connections which are being used over and over again, which is traditionally what we see, and then some other connections which sort of age out and spill into memory, we can get very, very high performance.
Okay, thanks. Kind of a related audience question. Somebody noted that Bluefield 1 had 2 memory channels and Bluefield 2 has a single DDR channel. Is that correct?
Yeah, that is correct. And in fact, the number of CPU cores on Bluefield 1 is actually 2x. So even though we've added more cores on the first one, and we actually cut back on the second one, those cores run faster. But the other thing we've found is that, as I was talking about, the on-chip memory, much of the caching that's required uses the on-chip caches, which are fairly substantial. So we can use those, and therefore we don't need as much external memory to support the 8 CPU cores that we have in the Bluefield 2.
Got it. Thank you. Another question from the audience is regarding how you can apply the IPU to containers and maybe manage them using something like Kubernetes.
Yeah. So absolutely. So we're really tightly integrated with the Kubernetes community on the orchestration here. When a key part of that is what's called CNI, which is the container networking interface. We've done a tremendous amount of work there. We're seeing, and we've published a lot of that work, both in the open source community for Linux, but also written some white papers about how to do that. So absolutely, it's we're really working on that automation piece. And the key here is not to try to do it all ourselves, but to integrate with the Kubernetes community and Mesos.
Great, thank you. Interesting question, and maybe this ties into the Rambus talk as well. Do you see any move towards independent testing or certification for secure edge implementations?
Yeah, I think that's a really good question. From a past life, we go through our own internal, we hire people to go try to crack our systems. There is certifications that are available, FIPS, for example, and common criteria. Those are common things that I think will happen. Whether there's an edge version of that that's developed, I think remains to be seen. I think it may be suitable, for example, in my past experience was with smart meters, and getting through CCIR and FIPS meant that that's an edge application that we really hardened that. So I don't know that we'll need a separate one for edge. Just assume that anything that you plug in to one of these IO processors is potentially malicious. And if you do that, and then you validate things, and you have authentication, and you have a secure root of trust, and you don't open up any of the networks, even if somebody plugs in, until it's been authenticated, I think you have to assume the worst, because in an edge environment, it's going to happen.
Yeah. A related audience question here was regarding that secure root of trust you mentioned. I assume that's probably licensed IP, correct?
Yeah, part of it's licensed and part of it we extended. So we have the secure root of trust functionality that's inside of the ARM core in terms of some of those things, but all of the secure boot as well as a whole bunch of the private keys and public keys that we do for secure firmware updates. You know, when you do a secure firmware update, the reason you're doing that is because you've patched a security hole, then you also need to prevent rollback. So you can't go backwards from, and that may be properly signed for the first generation of firmware, but if you're patching it because you found a bug, you need to prevent those rollbacks. So there's a lot of features that we've added internally to our hardware root of trust that enables all of that.
Great, thanks. I've got a more kind of broader question in the smart NIC space I wanted to ask. I'm interested in your view, particularly given Mellanox has some direct experience here, on the role of FPGAs versus, you know, a Bluefield or software programmable type SoC.
Yeah, so we get asked this question a lot. We actually sell a product line that's called Innova, which is FPGA based. Our original plan for that was to make that a general purpose smart NIC that we would provide to customers and let them actually develop software on top of that. When I say software, I should use air quotes here. It's really hardware. There's no difference between developing an FPGA and developing an ASIC at the end of the day. You need to develop Verilog, you need to close timing, and you need to make sure that it's bug-free. That's extremely hard to do versus writing software. And I just ask people, how many C programmers do you have in your company, or Java programmers, or whatever the language go, versus how many Verilog, RTL, chip designers do you have? And as a result of that, I think, at least from our perspective, we found customers could not build their own FPGA-based solutions. The only thing that they were able to do is take things that we gave them. And in the case, the first thing that we developed was actually some compression software or hardware in the FPGA and security, IPsec, AES, TLS. And once we'd done that, we very quickly implemented that first in our ConnectX-6 DX and then in Bluefield 2. We look at the FPGA as a great prototyping platform for a technology waterfall that ultimately drops into our ASICs. ASICs are always going to be cheaper and lower power and more efficient and higher performance than FPGAs. So frankly, the FPGA for us has become a really great prototyping platform, and then we implement that in our ASICs.
Got it, thanks. One final audience question here. There's a question about cloud-based vRAN and the challenges with low latency. When you see a challenge in terms of, I think this was in reference to your vRAN slide, isn't there a challenge in terms of implementing the vRAN in the cloud with regards to meeting 5G latency requirements?
Yeah, so that's one of the pieces of magic that the IPU does. So it depends on what you're talking about latency. There's some latencies which are 1 millisecond and 10 milliseconds. Those are not too bad. The ones that are really hard are the synchronization of the PTP clocks. And there you're talking about, 10 nanosecond, 20 nanosecond sorts of latencies. And there we've done some magic with our ConnectX-6 DX and Bluefield 2. We'll talk some more about that later. But yeah, it's frankly impossible to meet that sort of latencies if you're talking 20 nanosecond latencies in anything that's software defined. You take an interrupt and you're done. You can't meet that timing. So you need hardware support for that level of synchronization. So I don't exactly know what the question is. The tens of millisecond latencies you can meet with software defined. When you talk tens of nanoseconds, you need hardware acceleration and real-time control, and we provide that.